Yeah, hi everyone, I'm Junwei Deng from UIUC, and welcome to our 6th meeting. So today I will present three data attribution papers around the one of them is about the data selection like we have in our previous meeting, and two of them are more like the new I will not say new, but like TDM methods work on the generative AI. So today we will just go through the whole content like this. So first of all, the three papers we will present today will be, I would say, very different TDM methods. So I will try to introduce with a large picture of the modern TDM methods on the generative AI. So I will introduce in what place of will the today's three papers be within this big picture. And then after that, I will introduce two TDM methods and one and one application. Okay, so we have introduced a lot of the data attribution methods in our previous 5 meetings. So I would try to categorize them into three different data attribution styles. So they have different ways to calculate the influence of different of the training samples. So I would call them, the first one is the marginal based. Some of the examples are like you directly calculate the leave one out influence, or use the Shapley values, or calculate the Shapley values. So basically what they do is they directly calculate the marginal gain with one or the group of training samples removed. So you can see in this formula, I just write the leave one out to be an example. So you kind of want to retrain two different models. The one is on the full data set, and one is on the full data set with one of the data samples removed. And then you calculate the difference or the gap between the performance output of these two models on the test data point, and then you got the influence of that data sample. So basically, this is called marginal based, or I call it marginal based, but it's not really suitable for the generative AI because, as you can see, you need to train a lot of the models. Like here, for each of the training samples, you need to train one model that is with that data point removed from the whole data set. Okay, another one is the gradient based. We talk a lot about a lot of methods that is based on this one. Like the influence functions, the tracking, and the track, and I would say many other TDA methods. So so basically for this method, they capture the gradient information. So those gradient information are mostly used to calculate the Taylor approximation of the loss change, so that you can know how the parameter changes if one of the data samples are removed from your whole data set. So here the formula here I write is for the influence function. So I guess many of you are very familiar with this one. So it just so most of the methods is calculate the gradient of the on the training on one of the training samples and the test samples, and calculate Hessian matrix. Or some of the methods may not calculate the Hessian matrix, or but it's all based on they all calculate the influence. We can categorize them like the gradient-based TDM methods. And the third one, we will talk the third one as a simulation-based. So I want to introduce it first. So previously, we talked about the data models. This one can be calculated as a simulation-based model, and simulation-based TDM methods. So here, for the simulation-based, it means that it really do not care about the gradient information. It basically want to build another proxy or meta model to directly predict the model's behavior that is trained on the arbitrary data sample or data groups. As here, we have this M as the proxy model, and it takes the test samples X and maybe a subset of your training set as the input, and then it directly output the performance matrix of the trained model on that subset and the test samples. So here we call it simulation based, and the key of this simulation based TDA method is to how do you train this, or how do you build this proxy model. And for the data models, we build a linear model on the existence of the data samples, right? So today we will see some of the other methods that are still use this kind of the style to calculate TDA, to calculate the training data attribution, but a little bit different. So as we see, we have three different styles to calculate this data attribute. But yeah, basically today we will only talk about these three. And for this, for the different TDA methods within methods, we may have to collect some of the informations during the training, that just collects the information from the final training checkpoint. And for the simulation-based method, they may collect some information during each step. So here I want to quickly go through some of the information collections difference. Like on the right-hand side, we may have two different levels of the information collection process. The first one is the checkpoint versus the steps. It means that some of the methods may need to collect some information like the data samples trained on that step, or the evaluation matrix evaluated after that training step, or the gradient or the Hessians. Some of them need to collect this information for each training steps, like this, each circle in this plot. And some of the methods may only need the final checkpoint, like the influence function, like the track we talked about earlier in our earlier meetings. Like this, they only need this last data point. And some of them may go the intermediate way. They may need a few checkpoints during the training. Maybe they don't need every checkpoint for after each step. They may only need maybe the third, the sixth, and yeah, the last one. Yeah, and so like the tracking. So another level is ensemble numbers. So basically, most of these ensembling methods are to handling the training randomness. So it means that it may not only train the model once, like this green, like this one shows in the green. They may train the models different multiple times, like represented in different colors. So it generally works for most of the TDA methods to improve their effectiveness. But actually, some of the TDA methods may natively needs more assembly numbers than the others. Okay, so with the first, we classify the styles of the TDA method, and we then will state the difference between the information collection process, that is on two levels. The one is the ensemble number, and one is the information collection level from the step. That means that you need to collect some information for every step. And the checkpoints, that means that you need to only need to collect or calculate the gradients or collect some information from the last checkpoint. You can see we can maybe identify or locate some of the methods we talked about in our previous meeting, and some of the methods we will talk about today in this picture. So the style is encoded in the color, and they basically locate like this. As you can see, some of the TDA methods we are familiar with are the influence function. They only need they can be calculated with only one checkpoint, and they do not need to collect the information from each step. And some of the methods like the tracking ideal, they calculate the last difference. for each step, and some of the methods may goes to the intermediate way, like the tracking checkpoint method. And like the methods we talk about, like track, they only need to calculate for the last checkpoint, but they may need a number of the assembling to make it work. And some of the methods we Jihan showed us, like in the third meeting, it's about the source. It's just need to calculate maybe a bunch or a few of the intermediate checkpoint during the training and to do some assembling. So it's basically located here. And today we will introduce 3 of them. The first one we will introduce the rapid aim, which basically a very easier version or a computing efficient version of the tracking. And another one is a GPT influence. It's a simulation-based method. And the third one is the data models, one of the applications of the data models. So for the data model, you may recall that it needs to train a lot of the different models on the different subsets. And for this GPT influence, it will be a very I would say a very different one. It need to collect some information during each step, and build another simulation model to predict the behavior of the to predict the counterfactual behavior of the model. Okay, so yeah, let's maybe jump into our first paper.
Hi, Junwei. So sorry for the interruption. If you don't mind me asking a question.
Sure.
So for the simulation-based model, as you mentioned, is the simulation model tries to approximate the original trained model, or try to directly approximate the score you care about?
Oh, I would say, let me think. For the simulation-based model, you may have different kind of the proxy models or the meta models like this M here. For the data models we talked about in our previous meeting, it's a linear model. We'll calculate based on the existence of the data samples in your training samples, right? So the score is actually the weight or the parameter of that linear model, and the output of this model is the I would say the performance matrix of the model trained on that subset. That is this is AS here. So yeah, so basically on that, in that data model's case, the score you want to calculate is actually the weight of your simulation model, that is this M. And today we will present another simulation-based model. That is, it built a model that I would say simulates the whole training process. That is that is the evaluation matrix or the performance matrix in each step. And basically, if you have this model, you can predict predict the behavior of that of this AS on each step. So basically, you've got your data attribution results. It's not like really like a concrete score. It basically means that you can simulate the whole training process, and you got the final like a final performance matrix after that.
Okay, thanks.
Oh, okay. So I will jump into our first method today. As you can see in these two dimensions, you will have maybe a really low computation cost on the left bottom side, and you will have a relatively higher computation cost on the right on the right top. So it's okay, maybe different methods have different formula or different ways to collect the information. Maybe they still have different cost, but they generally may seem something like this. So as you will see, that the experiment the experiment did by this rapid-in will be somehow on a larger model than this GPT influence and data models here. Okay, so another thing I want to restate is that there's some challenges for basically all TDM methods in the generative AI, right? You need to handle a large number of data samples because basically you need to calculate all the training and test pairs. And another thing is that you have a really large model that has a really large number of model parameters that the gradient-based methods we need to handle this. And some other things like for the generative AI or the large language model, you need to calculate maybe the token-wise attribution, and you may need to handle some unseen data samples. So basically, this is the motivations of today's 3 papers. Okay, the first one, the rapid-in. As we said, this is more like a computation efficient version of the tracking. So basically, if you understand what tracking does, it's basically what this rapid-in do. So the tracking method just calculate the gradient of the training samples and the test samples and use the dot product to calculate the score, right? So this one or use the cosine similarity to calculate the score. So this rapid-in will still follow this formula. Will still follow this closed form formula, and just use some I would say different ways to reduce the computation cost and to make it more suitable for the generative AI, like do some derivation to make sure it can calculate the token-wise attribution, data attribution. So what it do is you can just understand. I will go into some details about this, but what it do is that it divides the whole process into the caching and the retrieval. For the caching, it calculates all the gradient. It calculates the gradient based on all the training data point, and then they do some random projection and cache those gradients on the disk. And for the second part, it do the retrieval. They calculate the gradient based on the test data samples, and in the same way, and then it goes through all of your cached gradients you just did in the first step, and to calculate the gradient data on that one, and then you calculate the influence score based on the tracking's formula. So that's what the rapid-in do in their framework. So this will I will go into the details of this rapid-in. For the first one is about the token-wise attribution, and another one is their random projection method. So this token-wise so basically it did some mass derivation for the token-wise generation. But actually it's very I would say it's pretty straightforward here. It basically says that the first line is actually the tracking formula, right? So this so this T is the test or target samples or the target generation, and this SK is the training generation. So here you calculate the dot product between these 2 gradients, right? And if you want to calculate the token level generation, it basically replace the gradient of the gradient of the loss on the training sample and on the test sample to summation on each token of that training sample and as a 10 samples generation. So here you have 2 summation here, and basically here you can just understand that they see the generation probability or the generation probability as a Bayesian as a Bayesian style, which is the generation probability of the target sample is the product of the generation probability of each token in that sample. And then once you have the log likelihood, you will have this summation here. Okay, so basically that's the idea they have. Actually, in the papers, they did not mention this kind of thing, but I guess it is basically see the generation as a Bayesian process. and to see the probability as a product of the generation probability of the tokens. Okay, so this is about the token-wise attribution here, and another one is the gradient projection or the random projection of the TDM methods. So I put their methods on the third one, but we do have encountered some of the random projection to reduce the dimension of the gradient, from the number of parameters to some smaller projection dimension, like here I represent them as the K here. So we have encountered two of them. The first one is is more like the traditional gradient projection way. It is used in the track, right? It basically use matrix multiplication by this P on the gradients. This P is a random projection matrix, and it basically has the shape of the K times P, right? So this Gi is the gradient of the is a gradient you calculate based on the training samples or the test samples. It basically has the shape of this P times 1, and this P is the number of parameters. This K is the projection dimension you want to reduce from that number of parameters to this K. So this K should be much smaller than P. Yeah, so you do this matrix multiplication, so you have this calculation complexity of the OKP, right? Is that right? Yeah, that's right. Okay, so another one is the Juhan showed us in the I think in our third meeting. So you can do this by for each layer by an encoding and by an encoding matrix and decoding matrix, or encoding random matrix and decoding random matrix. So here you got this formula, and you got two different. This one is an encoding matrix, and this one is decoding matrix. And these two will have the different shapes, and after that you calculate them on the input sample, on the input sample, and the derivation on the output for each layer. And after that, when you calculate this one, you will have basically a complexity of the square root on the PK here for each layer. And this third one presented in this rapid-in, that is in this paper, is a little bit, I would say, easier to understand. It basically, first you calculate the gradient as normal, and then you do some normalization based on each layer of this of the gradient. This one is a flattened gradient, but you can still identify maybe some part of them are the first layer, belongs to the first layer's parameter, and some of them belongs to the second layer's parameter, and some of them belongs to the last layer. So they do this normalization within each layer, and the purpose of doing this is to make sure that there will not be one of the layers be especially important or have a larger values, or have larger gradient values. So they do this normalization, and they do some random shuffling, and after that, this different different gradient will be shuffled in within this flattened vector. And then they do the random projection. This random projection will use some red mature distributed random vectors, and then do some element-wise product on this gradient, on this shuffled flattened gradient. And then they do some summation with a sliding window style. Like the sliding window is the length of the sliding windows equals to the P divided by K. Sorry, it's P divided by K. So after that, we will have this shortened rapid this shortened rapid, they call this rapid gradient. Basically, you can see it as a random projected gradient here. So this one is I would say this one has the computation complexity with the OP here, and normally as we see that the this K is much smaller than P. So this OP is actually for most of the cases it will be larger than this square root of the PK. Yeah, so this is basically the three different random projection methods we have encountered in the TDM methods, or the TDM methods we've shown before.
So I was wondering, please go ahead.
Yeah, I just have a very quick question. Like, what does it mean by the -1 and 1 random projection here?
Oh yeah. This basically just means the red mature distribution. You have 50% to be -1 and 50% to be 1, and then you have this this red mature random vector. Right. For each element is a red mature distribution, right? And then you do element-wise element-wise product on this flattened gradient.
Okay, I see. Thank you.
Yeah, I think that they may need to write more like a vector here rather than a -1, 1 here, as would be more clearer.
So my question is, for the random projection to work, you only need to have some distribution like a random macro Gaussian. Does the author mention why do they want to use the layer-wise normalization and then do a random shuffling?
They did not really justify why they want to do this. For the normalized, they say that for the normalized, they say that they want to make one of those layers are too important or much more important than the other ones. And for this random shuffling, yeah, I'm not quite sure I mean, they did not really justify this, but I think this is will kind of like approximated behavior. Like if you really have a random projection matrix here, like this P, you will have this kind of like shuffling for the different for the different features you extracted, like for different for different features you extracted from that gradient. Yeah,
so,
you do this random.
Yeah, so my interpretation, like, is this this seems to be an operation that is equivalent to, okay, so like assuming like for the original random projection, right, the first row, the first bullet point, that is like if we are having random marker sample for that random matrix, so we are doing basically +1 and -1 applied to every element of the original gradient vector and then sum it. But it seems like what the last one is doing is like for the original random vector, no, sorry, for the original gradient vector, we first downsample the element to a shorter one, and then do a kind of like apply a smaller random marker random matrix projection for that. So this seems to be an equivalent operation with this, right? So basically, first downsample the gradient vector. I think this is effectively what the random shuffling is achieving. Right.
Yeah, I was wondering if it just to follow the tracking paper, then once we obtain a gradient, if they want to save the computation, then just apply any random projection matrix to both gradients and then compute the inner products, right? So that's a natural approach that would have been done. But the summation are commutative, so it doesn't really matter whether they do shuffling or not because it's a summation. I think the additional thing they did here is normalization. Essentially, that basically ensure each layer have the same norm. That's the point I don't quite understand, because it seems to me this will destroy the original structure. For example, the inner product will change even without random projection. The inner product will change after normalization. So it seems to me it's like a empirical, like heuristic they have found in practice. Is my understanding correct here?
Right, I agree. Like the normalization is definitely something irrelevant to the kind of run projection. Yeah, so yeah, yes, that might be something they found empirically useful.
Right. Okay, thanks.
Thanks.
Okay. Yeah. So these are the different random projection methods we met in the TDA in the TDA methods we talked about. So as you can so this is basically the technical detail for this rapid in, and you can see it's still following the tracking's formula. And so basically for the experiment or the evaluations they did for this method, they basically compare it with the tracking method. And of course, as you can see, it should be more it definitely should be more computation to be more efficient than the original tracking method. So here they do two of the evaluation to show that it basically can perform as well as or as good as the the tracking method. The first one is the so both of them are actually all so both of them are the error tracing. The first one is a backdoor attack tracing. So this backdoor attack tracing basically means that they first have a data set, a real data set, and then they or an instruction response data set, and then after that they change some of the data sets from the original one to a backdoor data samples. What they do is to add some special words in front of this instruction, like here they add howdy in front of the instruction, and then they change the response. The correct response or the original response should be something directly or correctly reply to that instruction. And backdoor data samples will have the response or extracted from science fiction. So it will be very, well, I would say, easy to identify that that one is not really a correct answer or yeah. So basically they change some portion of the data samples in the original data set to these backdoor data samples, and then they train a model. And after that, they will have this trained model and to generate some response based on the test instruction. And then we'll as you can imagine, some of the if you add this howdy, this special word in front of your instruction, the response will be most of the time the response will be something very similar or in the style of the science fiction as the backdoor response, right? So what they do is that they collect 10, the only 10 response that is affected by this howdy or this special word. So this response are actually some science fiction style response, and they track those attacked generations and to see if the highly influenced or the top K highly influential data samples are also attacked or are also the backdoor data samples. So normally speaking, you will imagine that those response that has been affected by the science fiction should give more attributions to the backdoor data samples, right? So here they just assume that you should track back to those backdoor data samples in your top K highly influential data samples of your TDA methods, of your TDA scores. So here they do the experiment based on different methods like the random selection, some similarity or embedding similarity method, and between the influence function tracking and their methods on this top 5 and to top 1000. So here this this task might not be a really difficult one because most of them are getting really large or really high the area under the curve, or the different on the matrix. So it means that for all of this method, like the influence function, trace tracking, and the rapiding, they both can track back to the black door data samples, and some of them are even track back to all of the highly influential data samples in the top K are the backdoor data samples. So here is it basically just want to show that their methods are as effective as the tracking, even though with that large dimension reduction by the random projection. And another one is error tracing. So this one, they build some synthetic data samples, and then they change some of the correct answers from the change some of the correct answers to the wrongly ones. So still they collect as they said, they perturb some of the data samples, right? So still they trace back the generation, those affected generation, to see if the highly influential data samples are perturbed as well. So well, this is kind of like still making sense, right? If you got this wrong answer, and then the highly influential ones should be those training samples that are perturbed as well, or in the direction of your response, in the direction of a wrongly response one. So this task a little bit it's kind of similar to the previous one, but the perturbed data samples are just perturbed by the sum of the tokens, like the name of the country. So here they only have three different types, like change the China to Canada, and yeah, there are the two of them. So for this one, they just use different methods like the previous one, but they add another trick that is TW here means the token wise. It means that they only track back the training sample that is highly influential to that specific token. I mean the China or Canada or India or Japan. So here for this, as you can see, this methods labeled by this token wise, they are actually much higher than the methods with not use the token wise or the tracking or the influence function. Yeah, so this is basically the evaluation of this rapiding method. Okay, so I'll move to our second paper I need to present today. I just stop here to see if there is any questions. Okay. So I'll move to the other to the second paper. That one is the simulation-based method. So just to recall, the simulation-based method is just to you want to build a proxy model. That this proxy model will take the test sample and the training subset and then to output the performance matrix of the trained model on that subset and on that test samples. So we talked about these data models before, but today we will talk about another one to build another to have another design of this proxy model to complete the job. Yeah, so here this paper on training data influence of GPT models. They train the simulator to simulate the training trajectories of the whole training process. And I will go into details about this one. And as you can see, you need to, when you want to train the simulator, you will go through some normal process as if you are training a normal machine learning model or deep learning model. You need to collect some information that is but here you need the data you need to collect is the training dynamics of the GPT or the model you want to do the data attribution on. And the second one, you want to train your simulator, use the model collected from your step one. And the third one, you will do some influence. You have your model, you have your trained simulator, and then you can try to use it for the inferencing, right? Someone gives you a counterfactual, give you a counterfactual prediction task that is with one of the test samples and with a subset of your of the training samples, and to ask you, okay, how will this model behave? Okay, you use your simulator to tell them, okay, so on this test sample, this training subset will behave like better or worse or something like that. Yeah, this basically follows this pattern, right, for the simulation-based method and for this paper. Okay, so first, I will just split it into 3 parts. The first is about the collect the training dynamics or the data collection part for the simulation model or for the simulator here. So in the paper, they call it the training dynamics collection. So what they do is that they use a subset for they retrained independently retrained k different models. This k should not be a really large should not be a really large data. Should not really be a really large value. So it should be something like 10 or 5 or something like that. Yeah. And for each independently trained model, they use a subset, and then they train model as normal. And during the training, one thing, the only thing they do is that they record the dynamic of that. They record the dynamic of that training process. That is, for each step, they record 2 things. The first is that which data batch are actually used in this step. For each step, you may use maybe 4, 8, or 32 data, right? So first thing they need to record is this. And another one is the performance matrix evaluated after that step. So this I just used the Y here to represent that. So the performance matrix can be the loss of your loss on the test set, or can be some other matrix you want to use on the test samples. So after you train each model, you will have a dynamic. You will have this training dynamic, right? For the first step, you use this data, and you got the training performance, the performance matrix like this. And for the second step and for the last step, so we have this dynamic or training trajectories for the model for this model training process. And then you retrain maybe k times to collect more data on that. Yeah, that's basically the data collection for the simulator. And for the second part, is how do you train this simulator, right? So they build this simulator like this in this diagram. So they would take the training batch of that step and the performance matrix of the previous n step, like here. This is the previous 1 step, and this is the previous n step. And then you take all of these things as the input, and then they build an nth order Markov model to like this. And then, as you can see, this is basically, they say that the performance matrix after this step should be a linear combination or a linear compilation of the previous n performance matrix and the bias here. So this alpha j and this beta, this alpha and beta are based on this the training batch of this step, and they are trainable. And so this alpha and beta are actually calculated by the fabulous inner product of the hidden embedding of the training samples and the test samples. For the hidden embeddings, they basically use some pre-trained models like the BERT to calculate the hidden embedding. and to use some trainable parameters to do some transformation and to calculate the fabulous inner product here. And yeah, so basically it works like this. And if you train them and this model or this trainable parameters are trained by the L2 loss based on the some regression training loss like the MSE here. And the data you use is actually the training dynamic you collected from the step 1. As you can recall, you have this training batch and the performance matrix for each step, right? So here you can just train it like this one. Use the data collected in your step 1 here. Yeah, this is the step 2. That is, how do you train the simulators? And step 3 is just use this simulator like this one to do some inference. So as you can see, this simulator is actually calculating the performance matrix, like the loss, after each step. So basically, if you do this iteratively, you will have the training loss or the performance matrix for after each step. You will basically have the loss trajectory or the training trajectory here for the whole training process. Yeah, and basically this model is really as you can see, it should be very quick. Can be calculated much quicker than the real retraining. And here these are the 4 different experiment settings. They compare the different methods as well as the ground truth, that is, you actually retrain the model and to see the training trajectory. And as you can see here, this performs, I would say, surprisingly well. The dark blue one, I don't know if you can see it clearly. The dark blue one is the ground truth, and the orange one, or orange to red one, is their method, or their simulators result. As you can see, this training trajectory is really kind of close to the real one. Yeah, so as you can recall, that this simulator is actually trained based on the real retrained models data, retrained models dynamics by the MSE loss. So basically, you can see it's like more like a time series forecasting or something like that. You are doing some regression problems here. Yeah, so these are the 4 different settings. The first 2 are the loss. They take the loss as a performance metric, and and for the last 2, they take some other evaluation matrix as the performance metric, and the performance will basically, yes, yeah, basically well here.
Did they report like how many samples do they need to train this kind of estimators? So basically, how many like for the D run, right? Like you need to collect multiple retraining in order to ask, like in order to
yeah,
this speed, right? So many.
Right.
How many training trajectories they need to collect in order to?
I can find them, but I really forgot that one. They should specify how many data they collect. Okay, so yeah, it's hard. Yeah, I can. Maybe I can find it after the print.
Yeah.
I think
I can also check.
You mean this number of K, right? This
Right.
Yeah. I remember it should not be large, and they. Yeah. Let me find
for
it
data models, you need. I would say data model seems to be a simpler task, right? You don't need to feed a trajectory, but you just need to feed a kind of mapping between the sets to the final performance. But still, like they need tens of thousands
Right.
retraining to feed the data model well. So this seems to be a harder task because you need to feed a trajectory. But since you're doing experiments on language models, I would imagine that it shouldn't. Well, I don't know what model they use. Like if they use maybe BERT or even smaller model, then maybe it's also kind of computationally feasible. But if they use like medium parameter models, I think it's already kind of expensive to have like more than thousands, right?
But one of the difference between the data models and this one or the previous work of this one, like the SGD influence, or something like that, or the same influence here, is that for each retraining, they may collect more data than the data models. For data models, you just collect the information of the final checkpoint, right? You train the model and you just calculate the performance of the last checkpoint. You know that, and different models are calculated by different subsets, right? And then you fit a linear model here. But for this, for this ones, they can just collect maybe a lot of the data during one training process because they just need to they just record this dynamic, right? The training dynamic run. For each step, they record this which training batch they use and what the performance metric is. And for this dynamic run, this is actually we will a lot of training samples for this simulator, right?
I see.
This dynamic run should be like have the same length as the number of steps.
Okay.
And for each for each training data sample for this model, you only need you basically have a sliding window on that training dynamic with the length n, right? With the length n. So here you will have multiple training samples for this simulator within one retraining process in the step one. So that will help the data collection, I would say. And and they have another assumption, that is, if you have a similar, you have a close or a similar data embedding based on some off-the-shelf language model here.
Right.
If you have the similar ones, you should have the similar effect to the model you trained.
Right.
Yeah, this will helps to generation. Well, they say that they will help the generation to some unseen data, but yeah, that's true. So this may help to collect less data to build a more accurate simulator.
Yeah, that makes sense. So another question I have is, like, when they do this evaluation, do they kind of use their simulator from scratch? I mean, for example, their 100 step, right, will accumulate all their prediction from first step to 100 step. Because it's kind of amazing that they're like, if you look at this figure, this plot, so their performance is even getting better for some later training steps. Because I would expect, like, because when you're accumulating these predictions, right? So there might be some kind of errors being accumulated. So expect like the curves will the curves will kind of diverge more for later training steps. But here it seems it's not. So I'm wondering, like, whether when they're doing the evaluation, do they accumulate all their predictions from scratch, or they just evaluate one step further? So, for example, when they are evaluating maybe one as a step 100, they kind of use the ground truth of maybe step 99 or maybe step 90, something like that, to and then on top of that, they just do one step prediction.
Yeah, I understand that. They say that they do this iteratively. That basically means that the errors may accumulate.
Yeah, everything is based on their simulation.
Yeah.
Okay.
And another thing that really confused me, but I did not really find something in the paper, is that they have really accurate 0 step here. I don't know how did they do that, because maybe they just calibrate all of the methods to be at the same point, because I'm not quite sure why all of these first steps are really accurate here.
I see. Yeah, thanks.
Okay. Yeah, this is basically the evaluation they did. They focused on the MSE loss of the training trajectory. And basically, if you imagine if the MSE is really low or the training trajectory is really accurate, you can basically simulate the training or simulate the training the training data attribution is really accurate. So so here is basically the evaluation here they provided. And I want to do some like in this one. I want to do some connection to the other simulation-based methods. One is a sim influence, that is the previous work of this paper, and one is the data models. But we have already gone through most of those things. The sim influence is previous work of this paper, and it only takes the last step's performance matrix as the input, as the input to build this model. So basically, you will not have those n different n last steps performance matrix. You will only have the real one last steps performance matrix to build this model. And the data models actually do very different things. They are trying to do an easier job, right? To predict the final steps performance matrix by a linear model or by some. They say that they do not restrict to the linear model, but anyway here. So this is like the connection to other simulation-based methods. Yeah. So I will go to the third paper we will need to present today. I will just stop here if there is any question to the second one. Okay. Another thing I want to point out is that the largest model here in this paper is 2.8 billion. It is the 2.8 billion model. It's still a really large one, but for the first one, like the rapid-in, they do some experiments on the, I remember 70 billion 70 billion model. So it's definitely larger, and as you can see, this simulator-based models will need more computation cost. So here they do some experiment, on the smaller models. Okay, so I move to the third one. The third one is this model-aware data set selection with the data models. It's more like a straightforward paper. So it's still try to resolve the problem for this data set selection. So I put the problems here. It's pretty easy to understand. It basically means that you want to find a subset of your training samples that the subset has a restriction, that is you only can choose maybe k samples in that subset, and then you want to minimize your test loss, right? Your target data loss. And for this DsDm, basically it means that they use the data model, they train a data model on that on the model you want to you want to do the data set selection, and then you choose the top k of the you choose the samples with the top k data model parameters, that is with the top k TDA scores for this data model. So it's basically straightforward to understand, and what you need to do is just to train a data model. It basically needs a lot of the training cost, right? You need to retrain a lot of model. You need to retrain a lot of models here. So the idea of this, or the method of this paper is basically clear. And I will not go to too much detail about data models again. And for the evaluation, they have two different evaluations. The first one is to for each selected training data set to train 125 million parameters, that is a GPT-2 style model, on the 6 billion tokens. The 6 billion tokens are fixed. Yeah, so here on 4 different on 4 different language model tasks, they say that their dataset selections are actually better than the random one, and better than the some baseline methods, like the to choose the related training samples to that that specific task. As you can see here, the y-axis is a log probability, so it's the larger the better. And here for the red line, it's a random selection. It's a random selected training data set on the same model, and this red dot line is a random selected data on a 10th larger parameters model, that is maybe a 1.2 or 1.3. I'm sorry, it's 1.3 billion parameter GPT here. So basically, they say that okay, their methods are actually comparable to the random selection with a larger parameter numbers model. And so this is for the evaluation of each different tasks. And another one is that they select 3 tasks overall, and that means that you need to select a data set that can be generalized or for broad model compatibilities, or for the and what they mean for the broad model compatibilities, it means that this data set should be this training subset should perform well on this 3 tasks overall. And it basically says that random selection is actually a really strong baseline here, but they're using the data models to select the data can make the performance better. And for those baselines only choose the related data samples, they actually are something even worse than the random selection. And for this paper, they do some analysis to the data samples, to the data samples selected by the DsDm, that is selected by the model-weird methods like the data models, and some of the other methods that only do the like the information retrieval or related sample selection. They say that I have 2 figures here. The first one on the top one is highly influenced, or the data samples that are selected by this method, and the bottom one are the data samples that are will not be selected, or the least possible to be selected by this TDM methods. As you can see, this they do some summarization on the preferred data samples of the DsDm. They basically say that the useful data, or the useful data identified by the data model, are not necessarily similar to the or similar to the target task. So and another thing is that the DsDm will really discards or don't use those mislabeled data in the training samples. And for those baseline methods, they basically discard those low quality data samples and use some high quality data or generally high quality tasks to be selected. And yeah, they do some analysis like this. Yeah, so yeah, this basically the data selection paper based on the data model. Yeah, I would like to present. Okay, so after that, I will just do a quick recap So today we present 3 different papers. The first is the Rapiding. As we said, it's basically more engineering way or efficient way to just do the tracking on the generative AI. To do some derivation to make it can be to make this data attribution can be done on the token wise, and of course do some special random projection to reduce the parameter dimension. And the second one is GPT inference. It's a simulation-based method. It basically builds an nth order Markov model to simulate the training dynamic and or simulate the training trajectories. And it uses some off-the-shelf embedding models to handle the unseen data points and to generalize the training process, or generalize the model they collect from the retraining. And the third one is the DsDm, that is a data selection method based on the data model. This is basically today's presentation.